Hello everyone, welcome to SQL Repository, and today we are going to discuss the wait type CxPacket and CxConsumer. This topic is very broad, so I have decided to divide this topic into two parts, and you are watching first part where we will discuss in and out everything related to parallelism or the parallel plans, so that you will be able to understand CxPacket and CxConsumer wait type properly. So what is parallelism? When multiple processors work together simultaneously to run single query, this is called parallelism. It occurs in SQL Server whenever SQL Server execute a query using the parallel plan. And in parallelism, you will find producer thread, consumer thread, and also you may find controller thread, which is the coordinator thread, and it does nothing. It will not process any record, it will not process any row, but it collects all the row processed by other thread. The query is executed in multiple threads, and the query can continue only when all parallel threads are completed. This means that the query will be as fast as the slowest thread. So among multiple threads, if one of the thread is slow, the other thread will have to wait. So your query will be as fast as your slowest thread. Now let's understand the parallelism using a ball game. Suppose you have 1200 yellow balls in a container, and this container has many other balls of all the possible colors in the world. Then you have the second container, and you have given a task to find all the 1200 yellow balls from this container and then move it to second container which is empty. Now one person is doing this task, then one person will count 3 balls per second, which means he will take 400 seconds, and this is equivalent to 6 minutes 40 seconds, right? So a person alone is doing this task in 6 minutes 40 seconds. Now suppose this container has been kept on a table and there are 4 seats. So now this task is assigned to 5 person. But there is a rule: out of these 5 person, whenever you will use multiple person to perform this task, you have to appoint one manager, and this manager will do nothing but only monitor the whole process and then synchronize the whole process. Okay, so you have 4 person left to count the balls. Per person will count 300 balls, and per person will take 1 minute 40 seconds. So at the end, if you will combine the time taken by each person, it will be still 6 minutes 40 seconds. But the entire duration of the task has been reduced, which is 1 minute 40 seconds. But there is a catch. As every person is counting the ball, then someone has to gather all the information and then sum it up. Then only you can give the total number of balls count, right? So this is the responsibility of the manager task, and manager takes 1 second to sum 2 sets. So there are 4 sets, so it will have to sum 3 times, which means it will take another 3 seconds. So actually the second scenario has taken 3 seconds extra, but the overall duration of the completion was 1 minute 43 seconds, right? So the overall duration has been reduced, but if you count the work hours of every person, they still had to work 6 minutes 40 seconds to count the ball, and then to collect all the information, manager also took 3 seconds. So this time we have taken 3 extra seconds. Now simulate this same situation in the SQL Server, where every person will become a thread, and then the seats will become the scheduler, right? And then in case of parallelism, the manager will become the controller thread. Now you have 4 threads performing the task. 5th thread, which is controller thread, which will be overseeing the entire process, and then at the end it will collect all the information, right? So in that case, the CPU time will still remain same, or the CPU time will actually increase, but overall duration of the task will decrease. Now just to simulate more with the SQL Server, suppose like you have the cache plan in SQL Server for the procedure. Suppose it's a procedure, and if once you have used the one scenario where you are using multiple persons to perform this task, then you will have to keep on using the same strategy. You cannot change the strategy in the middle. Now, in the second round, you have got the task to count 12 green balls. Now, one person is counting 3 balls per second, and one person can do this task in 4 seconds. But as you have to use the same strategy, then you will have to appoint 5 person, then one manager, 4 person counting the ball. Everyone will count 3 ball, which means they will take 4 seconds, but manager will take another 3 seconds to sum it up, right? So in the second scenario where you are using multiple people, it is taking 4 seconds plus 3 seconds. But ideally, if one person was doing this task, then one person can easily complete this task in 4 seconds. So because of the task was trivial, it was not a complex task, still you used multiple person, it actually increased the overall duration. So this is what happened in CxConsumer. When you are unnecessarily using the parallelism, then sometimes serial plans can give better output, can give better time of completion in comparison to parallel plan. But in case of procedure, because you have cache plan, SQL Server still go ahead and use the same plan, and sometimes it ends up taking extra time. Now, let's go back to the previous scenario where you had 1200 yellow balls and it was the ideal scenario to use multiple person. But suppose the distribution of yellow ball is not equal everywhere, and 4 person on that seat, they have few of them will have the yellow ball closer, few of them will have yellow ball not so close, right? So in that case, few of them may end up counting less number of yellow balls, and few will count more number of yellow balls. And in that case, few will complete the task earlier, and few will have to give some extra time to count all the balls. At the end, these are still 1200 balls, right? So in that case, suppose someone has completed the task only in 40 seconds and then other person went ahead and completed the task in 3 minutes. So the other person will still stay idle because it has to provide the count to the manager, and then it will sum it up, then only task will get over. So even the other person cannot do anything. However, the other person has counted all its ball, but it was less, and that person has completed early. And if we'll consider the same scenario in SQL Server, suppose you don't have the proper stats, so SQL Server has no way to identify that where exactly you have the data. So in that case, SQL Server can give uneven distribution to each thread, right? And in that case, some thread will end up fetching less number of rows, and some will end up fetching too many number of rows. And then in that case, the thread that is fetching more rows will take some extra time, and then other thread will also have to wait. So because of this uneven distribution, the duration will increase, because as I've already told you that the parallel plan is as fast as the slowest thread, right? So if your slowest thread is taking 3 minutes, then it will take 3 minutes. All other thread will have to wait for the entire duration. Doesn't matter if they were already completed after 20 seconds, 40 seconds, or after a minute, right? So this is one of another scenario where you will see CxPacket wait type in parallelism, and sometimes it will give you the problem in your SQL Server. Okay, so these are not the only scenarios where you might get CxPacket wait types more, and particularly the problem with the parallelism. There are many other scenarios as well, like as I've already mentioned in this game that you have 4 seats. Suppose now in the same place you have multiple games and other people are also playing those games, but you have total 4 seats. So whoever will take the seat will can perform the task and count the ball, but they will have to leave the seat after a certain time so that other player who is involved in the other game can also take the seat and perform their task. Now suppose this seat is equivalent to scheduler, which is nothing but CPU. So every CPU will have a big CPU queue, and then every task will go back and forth in the CPU queue, and then they will have to wait for CPU queue to become available again. So in that case also, suppose if for some reason in one scheduler CPU queue is too high, and in another scheduler CPU queue is less. So in that case, whatever thread is running in that particular queue where the queue is already less, they will get more, early CPU. They will go under running status very early, and they can complete their task in the less duration. But then on the other hand, there is another thread which is on another CPU or which is in another scheduler where the queue is high, and then after a certain time it will have to leave the seat, come back, then wait again for for its turn, and then go again to seat, count the ball, come back. So in that case, say same scenario in the SQL server where the thread will go to CPU, come back, go again, come back, and because there are too many tasks, it will have to do it multiple times. That particular thread may take more time. Okay, and this is very common in SQL Server because SQL Server assign these threads in a round robin method, and some of them can complete early, some of them may take more time, and then in that case sometimes CPU queue may become unbalanced across all the CPUs. So this is the another scenario where you may see CxPacket wait type, and particularly parallelism will become the problem. But most of the scenario that we have discussed here, like uneven distribution or uneven distribution in the CPU queue, one CPU queue is high and one CPU is very busy, and thread there in that CPU queue has to wait for more time. This is not exactly related, the problem is not exactly related to parallelism. However, it is related to parallelism because all the threads are related to parallelism. But the problem exactly is not related to parallelism. The problem is lying somewhere else, right? So this is exactly what happened with the CxPacket wait type, and in the next video when I will discuss CxPacket wait type, I will cover this thoroughly. But for now, you just have to understand that these are the different scenarios where you may feel that the problem is with parallelism, but the problem is not with parallelism. Yes, the other scenario where you had to count only 12 balls and you still had to go with 4 people, and then you ended up taking more time. This is the problem with parallelism. This is where CxPacket or excessive parallelism is the problem, right? So there are few ways to control the parallelism. Like you have particularly two settings in SQL Server, which are cost threshold of parallelism and max DOP. These settings are not very straightforward, and then when you deploy a SQL Server, by default cost threshold of for parallelism is 5, and max DOP is 0. 0 means there is no restriction, it can use any number of scheduler, a query can use any number of scheduler, right? And the cost threshold for parallelism is also 5, which is very less. But there is no particular number, or there is no hard and fast rule to set this number. You have to identify the correct number for your environment, right? So let's go ahead and look at a demo, and then we will come back to this sheet. But yeah, let me cover a few more things before going to demo. In parallelism particularly, you will find these 3 signs. And these 3 signs belongs to parallelism, but for the different stream. Like this first sign, it belongs to gather stream. The second sign, I've written this wrong here, but it is repartition stream. It is not gather stream. And then the last one, it is distribute stream. Okay, So the gather stream, as you can understand from the sign itself, it converts the parallel plan into the serial plan. The repartition scheme, which is the middle one, it actually swap from one stream to another stream. You will understand this better when I will cover CxPacket in the next video. But suppose just understand it in this way. Your plan is transitioning from one parallel plan to another. In that case, you will see parallelism gather repartitioning stream, right? Okay, then you have distribute stream, and you will see this sign of distribute stream in your query plan when your plan is transitioning from the serial plan to parallel plan. Okay, so let's go back to a small demo, and then we will come back and then we will discuss these few interview questions. Okay, so let me go to SQL Server, and here you can see a plan. Actually, let me go ahead and run this. I've selected the live and actual execution plan both, and let me run this query. And here, as soon as you will be able to see live execution plan, you can see parallelism here, and then here as well. But here you can see these are the repartition stream, and here it is gather stream. Okay, so the other stream, which is distribute stream, which is not too common, but you may see that particular stream of parallelism in your query plans in your environment. Okay, here it is not available, but you can see other two stream, which is gather and repartitioning stream. Now you can see that okay, so it is complete. Complete, but if I'll run it again and let the live execution plan come, okay, so you can see this part is already complete, but this part is not complete yet. After the sorting, get the stream and then select, this is still working. So this is where you will see the CxPacket weight type. But I am not gonna show this in this video. In the next video, I will show the CxPacket weight type here. But let it complete, and then we will go to the actual execution plan, and we will discuss few things. Okay, I cannot show these things in the live query plan because it does not contain all these stats. But as we have the actual execution plan available, so let me first go to this select. And here you can see the estimated subtree cost is 57.3927. Okay, so it is already more than the cost threshold for parallelism for for MySQL database instance, and this means it qualify for the parallel plan. But it qualify doesn't mean SQL will use the parallel plan. Now it is up to the SQL optimizer if it want to use the parallel plan or not. It find it worth to use parallel plan or not. Now in this case, it finds it worth to use parallel plan, and this is why it went ahead and used the parallel plan. Now let me go ahead and select the property of this select and go down completely. Here you can see the weight stats, right? So let me come down. The first one is CxPacket, second one is async network IO, which is another weight type that we will discuss in upcoming videos, and the third weight type is CxSync_port. So I'm using SQL Server 2022 right now, and SQL Server has introduced two new weight types from CxPacket weight type. Actually, it is driven from CxPacket weight type. Earlier you had CxPacket weight type only, and then SQL Server introduced CxConsumer weight type from SQL Server 2016 SP2 and SQL Server 2017 ATM CU3. After that, CxPacket was split into two parts, and there was a new weight type which was CxConsumer. It was supposed to be a harmless weight type, but this is not quite harmless, because in some scenarios we have seen that this weight type is something which we need to analyze because it was creating the problem. Okay, so it is not completely harmless, but in many scenarios you can ignore CX consumer wait time. Then from SQL 2022, there are two new wait types which are CxSync_port and CxSync_consumer. I will cover these wait types also a bit, but there is not much information available on these wait type. I have particularly seen CxSync_port wait type, so I can cover this, but even I don't have much idea about CxSync_consumer wait type. So once I will get more detail on this, I will create a new video on that wait type. But for now, we will discuss these wait types where I have enough idea. Okay. So now I will go to this repartitioning stream, and here you can see the actual number of rows, and you can see thread 0. Thread 0 is nothing but it is your the manager thread in the ball game. Here it is known as controller thread, and it does nothing. I mean, it does something, but at least it will not count the row. But there are other 4 threads which are counting the rows, and then it will give those count to your controller thread. Then controller thread will process it further. Now you can see the distribution is not not matching, because you can see thread 1 has processed 1561 rows, other threads 788, 709 and 980. But these are not too many rows, so that's okay. But if I go to the other parallelism repartitioning stream, and if I will expand it here, the number of rows were more. So this is why you can see the more difference also. One thread had to fetch 28,000 plus rows, and there is one thread which is thread 3 which has not even fetched 19,000 rows. So there is a difference. So obviously thread 3 can complete early, and thread 1 may take extra time, and it will show CxPacket wait time. And similarly, if I go to hash match, or let me go to actually sort and expand this again, and here you can see a major difference, because thread 1 was processing more than 704,000 rows, while if you look at the thread 3, it has processed only 177 plus thousand rows, right? So there is a major difference, and because of this difference, you will see CxPacket wait type which is problematic. Okay, because it is not the optimized parallelism, because there is a huge difference between the number of rows counted by or fetched by or processed by different threads, and we will discuss what is the problem here in the next video. But for now, we will go ahead and discuss few of the interview questions related to parallelism. So what is parallelism? So this is the something that I have covered in the very first line, and this is here: multiple processor work together simultaneously to run single query. Oops, I have written the spelling of single wrong, so excuse me about it. Now let me go back to the questions again. Oops. Okay. And what are producer and consumer thread? So producer thread which actually scans the data and bring it to buffer, and then consumer thread consume those that data from there, right? So this is what they do, and then there is a controller thread, and you already know it does perform the synchronization. It will not process any records. It will just monitor the whole parallelism, and then it will synchronize. Right. What if queries? Okay. So what decide if query should use parallelism or not? Okay. So as we have already discussed about cost threshold of parallelism, which is here. Okay. And if I go to advanced, you can see I've set it to 1 for now. It is just for demo purpose. It is definitely not a good number. So cost threshold for parallelism is 1, and until the subtree cost of your query. So if you will have to check the subtree cost here, which is 57.39, until it is not more than cost threshold of parallelism, SQL Server cannot make a plan, use a parallel plan for any query, because it is not satisfying the configuration of cost threshold of parallelism. This is one thing. But let me actually go ahead and comment this order by here and execute this. So here you can see that there is no parallelism or operator, because SQL Server is not using the parallelism. But if I look at the subtree cost here, it is 2.83, and if you remember the cost threshold for parallelism in my SQL instance is 1. It is still more than more than that value. It is right now 2.83, and cost threshold of parallelism is 1. So SQL Server, if it want, it can still go for parallel plan, but estimator has decided not to go with the parallel plan because they think that serial plan would be much better in that case. Okay, let me uncomment this. So which means I've already ordered my next question: will parallel plan always use maximum degree of parallelism? No, it will not use, because actually I did not answer of this question. Let me answer it. But there is one more question, which is, will query always use parallelism if query cost is more than cost threshold for parallelism? So the answer is no. If the subtree cost is more than the cost threshold for parallelism, it doesn't mean that the query will use the parallelism. Now it's up to the estimator, SQL estimator, if it want to create a parallel plan or not. And if it feel that parallel plan would be beneficial, it will create the parallel plan, and it also depends on the availability of CPU. Okay, but if it will not feel that it should create the parallel plan, a serial plan would be much better, then it will still go ahead and create the serial plan. Now let me go back to this question again. Will parallel plan always use maximum degree of parallelism? So suppose in my case maximum degree of parallelism is 0, and I have 4 CPU cores. But it doesn't mean that all the plan will use all these 4 CPU core. Maximum, if you have maximum degree of parallelism and as 8, but your query plan is not using all the 8 CPUs, it is not a big deal, because it is up to SQL Server what it decide, and it can use less number of CPUs, less number of schedulers than the value of maximum degree of parallelism. But yeah, it cannot definitely exceed. If you have given the max DOP as 2, it can maximum use 2. If you have given 4, it can maximum use 4. But it doesn't mean that it has to use 4 every time. Right? So I have answered this question also. So I have only these questions related to parallelism, but if you have any question, you can write an email to me on sqldepository@gmail.com, or you can also leave a comment in this video, and I will try to answer that question. Okay, so this is what I wanted to cover in this video. In the next video, I will run the same exact query again, and then I will discuss the CxPacket wait type and what exactly is causing this CxPacket wait type and how to resolve it. So I will see you again in the next video of CxPacket. Thank you for watching this video.